All right, welcome back, Algebra 2. We are going to be starting a new unit today, and that is Chapter 7, which is on exponential and logarithmic functions. Today we're focused on the first two sections here, which is going to be how do we understand and graph exponential growth and decay functions and models. So to start that off, I want to look at a quick website here to model exponential growth. So here's a type of compound interest calculator, and you may have talked about this in other classes. But this compound interest calculator takes in three things. It takes in how much money you'll save a month, what your starting age is, and then what interest rate you're going to get. So without going into too many specifics, we're going to leave our interest rate, which is a very important part of it, at 8%. You can't go to your local bank and get 8%, but if you were to invest money early on into the stock market for a long period of time, you could definitely get 8%. So if you look it up, the stock market averages around 10% a year if you look at the different indices. And again, this would be saving for a long period of time. So at least 10 years, but more like 20 years plus, you could expect that kind of return. So we're going to say 8% starting age. We're going to bring that down to, like you guys, 15 years old, and then monthly savings. So you also have to realize here that when you think about maybe your personal situation, you might not have a job or anything like that, and this monthly savings might be impossible because you're not working. But then understand later when you're in your 30s and 40s and you have a career that you'll be able to afford much more money saving into your account. So I'm just going to put in $100. So if you put in $100 right now at 8%, let's watch how your money will grow. And so you can see the graph show up on the bottom, and what you'll notice is the graph is not linear. There comes a point where the graph starts to shoot up more and more and more, and this is where the exponential function and exponential growth takes place. So if you put in $100 a year at that interest, by the time you're 65, and this is kind of a retirement calculator, you have about $800,000. Cool thing is, if you look at the amount of interest you get versus the amount that you put in, is pretty dramatic. So kind of a cool calculator. This shows us and demonstrates the type of function that we're looking at, which is an exponential function as opposed to a linear function. You can see the graph as well. It's not a line, it's a curve. And this function models well things that increase by a certain percentage. So this is a prime example of something that's very powerful, compound interest. And so you can mess around with this calculator if you Google. Well, the one that I'm using is just called Econ Ed Link Compound Interest Calculator. You can play around with it, but you can certainly play around with the numbers and say, hey, what if I double that and go $200 per month? How would that change my outcome? So if we put in $200, we're getting instead of about 800,000 at 65. Would it be double? It would be, yeah, it looks like it'd be double. So about 1.6 million. So kind of a cool thing to look at there. And that sort of just introduces this type of function, an exponential function. So just kind of a review, we've already talked about linear functions quite a bit, right? That was in chapter 1 and 2. That was like y equals mx plus b. We talked about quadratic functions. That was y equals something like ax squared plus bx plus c. And now we're looking at exponential functions. And this is going to look more like y equals a times b raised to the x. So we're going to have this repeated multiplication that happens with this function. Some definitions to take care of right away. First one is exponential function always has this form, y equals a times b raised to the x. And we'll get to these specific parts a little later, but this a value is often called the initial value. The b value is often referred to as the growth factor. And we could also say that's the decay factor as well. The growth or decay factor. That's the number that we're continually multiplying by. So that could be something that's going up or something that's going down. Looking at specifics, if a is greater than 0 and b is greater than 1, then it's an exponential growth function that's going to start off slow and then increase rapidly. If a is greater than 0, but the b value is in between 0 and 1, then it's an exponential decay function. And that's where you're going to have some starting value, and then it's going to decrease rapidly and level off. So you can think of that as like maybe the depreciation of like a car, or the depreciation of something new goes down kind of rapidly in those first few years, and then starts leveling off more and more. The last thing, the last vocab term is asymptote. So that's ASYMPTOT. An asymptote is a line that a graph approaches more and more closely. Asymptote. So we'll talk about that in our graphs. All right, so one of the main things that we're going to look at in this section, just to introduce it, is how to graph these types of functions. So for this first example, we're going to demonstrate how to graph these functions just by using a table of values, just by plugging in points and looking at the result. So if you look at example 1, it's y equals 3 raised to the x. So if you think about, if you compare it to kind of our model, 8 times b to the x, our b value is 3. And technically our a value here is just 1. There really is no a value here. So if you classify this function, the a value is 1 or greater. The b value is also greater than 1. This is going to be exponential growth, right? Because this growth factor, the thing that we're repeatedly multiplying by, is a number that's greater than 1. So take any number and start multiplying it by 3. That number is clearly going to increase rapidly. So this is a growth function. And if we use a table of values, it's really simple. We'd make a x and y chart, and we would start plugging in values for x. So we could plug in, let's just start with 0. We'd say, what is 3 raised to the 0? Well, 3 raised to the 0 is 1, right? Anything raised to the 0 that we learned with exponents in chapter 5 or 6 is 1. So that would be a point on our graph, 0, 1. And we can plot that. So there's our first point. Now, of course, we could just keep on doing this. So we can plug in anything for x, right? If we can plug in anything for x, that means that the domain is all real numbers. There's no restriction on what we can type in for x. So let's just plug in another thing. So if we plug in 1, that means that 3 to the 1, well, of course, that's just 3. So we have another point that exists on the graph that is 1, 3. So 1 already goes to 3. And you can just by looking at the behavior of this graph, you know it's going to go off the graph really quickly. So if we go to 2 and we say, well, what is 3 raised to the 2? That's 9. So that means I have another point of not 1, but 2, 9. So 2 goes to 9. So that's already up here. If I plug in 3, it's going to go off the scale of this graph, but I know that if I plug in 3, well, of course, that's 27. It's going to go off of my graph, but it still exists. It's just going to be off my graph. What about negatives? So we can plug in negative values as well, because our domain is anything. I can plug in -1. So I could ask you this, what is 3 raised to the -1? Well, if you remember exponent properties, right, 3 raised to the -1 is the same thing as 1 over 3 to the +1, 1/3. So there exists a point that's -1, 1/3. So if I go to -1, it would be at this kind of like 1/3 mark. And if I plug in -2, I would have 3 raised to the -2. Well, that's the same thing as 1 over 3 to the +2, or 1/9. So -2 would be 1/9. So that's really just getting really close to this bottom line here. In fact, if you think about any negative number, or think of a really large negative number, like negative 100, well, is that going to be 0? We're going to have 3 raised to the negative 100. Well, that's the same thing as 1 over 3 to the positive 100. So you can see here that it's not going to be 0 because 1 over a really, really large number is not 0. But if we plug that into our calculator, we know it's going to be like 0.000000 whatever. It's going to be really close to 0, but not quite reach there. So what happens here, so this would be like negative 100 and then like 0.0000 ... basically almost 0. So we know that no matter what, we're never going to get to 0. No matter how big of a negative number I plug in, I'll never get to 0 because I'm always going to have 1 over that. So that's where an asymptote comes into play. So this graph, if we were to connect up this graph, we would sketch it like this. It would start increasing very quickly, and we'd have an arrow. It's kind of going up. And then this is going to level off right here. So I'm going to draw an arrow here just to signify that it's getting close to the 0 line, or y equals 0, but never quite reaches that. To indicate that we have an asymptote, or this boundary line, we can put in a dotted line right here. It's often what we do there is we put in this dotted line, just like when we did quadratics, we did like an axis of symmetry. We can put in this dotted line to show that the graph is never going to go below that asymptote of 0. Okay, so on this first graph, I'm going to say that y equals 0 is the asymptote, and of course that blue graph is our function y equals 3 to the x. And this is exponential growth. So I'm also going to put in here, because we always talk about it, the domain and range. You should be able to tell me what the domain and range is by looking at this graph. The domain is going to be all reals. It means I can plug in any number in for x, and I'll get some kind of output. But the range is not all reals. The range is going to be only positive values. If you look at the asymptote, we're only graphing things above 0. So my range is y is greater than 0 for my domain and range. Okay, so this is an example of taking a function, using a table of values, and plotting the function from that. All right, so let's look at another one of these. Here we have a function that's y equals 8 times 1/2 raised to the x. So again, this is an exponential function, and if we compare our model, we can see that the b value here is 1/2, and the a value, or the initial value, is 8. So because the b value is in between 0 and 1, and so the growth factor, or in this case the decay factor, is 1/2, think about repeatedly multiplying by 1/2. Take any number and start cutting it in half. If you keep doing that, obviously your number is shrinking, getting closer and closer and closer to 0. So this is clearly going to be a exponential and decay function. And we're going to use the table of values to do the exact same thing and plot this. So table of values, we're going to have an x and y chart, and we'll start with plugging in like 0. If we plug in 0 into this, well, we'd have 8 times 1/2 raised to the 0. Well, again, anything to the 1/2 or anything to the 0 is 1. So this is the same thing as 8 times 1. So this would be 8. So that means that my point, if I plugged in 0, I would get 8 as one of my points. 1, 2, 3, 4, 5, 6, 7, 8. So I have this point right here. And if I keep plugging in points, so let's plug in 1. Now I have 8 times, well, what's 1/2 to the 1? Well, now I'm just taking 8 and I'm multiplying by 1/2 one time, which is going to give me 4. So if I plug in 1, my outcome is 4. So 1, 4. So we have that. Go ahead and plug in 2. Well, if I have 8 and then 1/2 squared, well, that would be like starting with 8 and then multiplying a half twice. So take 8 and cut it in half twice. Well, 8 goes to 4, which goes to 2. Right? So now I know that 2 is going to output 2. 2 goes to 2. And you can keep on going with this, right? So 3, what happens when I cut it in half 3 times, or 8 times 1/2 squared? Well, without showing up, well, I'll show it anyway. 1/2, if I do that 3 times, that's going to give you 1. Right? You could plug that in your calculator too, but you shouldn't have to. 3 is going to go to 1. So we have this point. And it's going to keep on getting closer and closer and closer to which number? 0, right? If I keep taking some number and cutting it in half, right, it's going to get closer to 0, but never theoretically reach 0. So this is going to keep getting smaller and smaller and smaller. And so we can plug in maybe, I don't know, what if we plugged in like 8, right? What's 8 times 1/2 raised to the 8th? Let me just plug in this one. 8 times 1/2 raised to the 8. Well, that's 0.03125. So obviously it's getting smaller. 0.03125. So there's my point, and 8's over here, but that's going to be really close to 0. So we don't have to necessarily plot all these points. We know the general trend. If I were to sketch this graph now, it's going to start going down, decreasing, and then starting to level off here. It's still going to decrease forever, but it's going to slow way down, and it's going to look like it's leveling off completely, but it won't. It's just going to be going really, really slowly down to 0. And then can you plug in negative numbers? Yes, you could plug in negative numbers. If I plug in -1 in this case, I'd have 8 times 1/2 to the -1. Well, think about exponent properties again. This would be the same thing as 8 times, not 1/2 to the -1. That would be the same thing as 2/1 to the +1. We could take the reciprocal of that and make the exponent positive. So this actually goes to 16. So if I go to -1, it's actually going up to 16, which is way off my graph in this particular case. So -1 does work, and so does negative like 100, but that's going to be so far off the graph. So we're going to show that trend just by showing the arrow kind of going up there. So there's a sketch of my graph. I have the table of values. I just plug in x values and I get y values, and I plot those points. So notice the same thing happens here, is that we have an asymptote at 0 again. So we have this, imaginary dotted line here that the graph is approaching but not getting to, and that is y equals 0. So y equals 0 again is the asymptote. And again, just like we put before, the domain and range, right? The domain and range are going to be similar for this graph as well. The domain is all reals, and the range in this case is y is greater than 0. The only thing that's different here is that we have exponential decay, which is given by this growth factor being a different value. That b value being different is going to dictate if it's growth or decay, and that's it for these types of graphs.